So this technique is an implementation technique in which multiple instructions are overlapped in execution. A very good analogy is mentioned in your book, which is a laundry. So I assume that all of you must have done laundry in your life at least once before. If they are not mama's baby. I used to be, that's why I'm referring. Well, so if we talk about the laundry, there are 4 stages. The first one is you put the clothes in the washer. After washing, you have to put it in the dryer, and then the next phase is folding the clothes, and the last one is putting them in the closet. Okay, so let's say you start off your laundry cycle at 6 p.m. and you're going phase by phase, and you finish the first laundry in the first load by 8 p.m. So it took about like 2 hours to complete. Now if you have to do multiple loads, and if you're following this single cycle procedure, you would wait until the first complete cycle is finished. Would that make sense? Because once the clothes are washed, you put them in the dryer, and then you put the next load of the clothes into the washer, right? So that's the same idea that is being used in the pipelining concept. But here you can see, if you follow this one, so the total time for 4 loads would take 2 hours times 4, which is 8 hours to complete. Okay, and if you pipeline this thing, as we usually do, once the first cycle of clothes are washed and we put in the dryer, at the same time we put the next load cycle into the washer. Okay, so familiarize yourself with this kind of timeline. When the first thing is in the next stage, the next load is in this first stage. Okay, at this timeline. So you will see now onwards you will be looking at similar kind of diagrams. We will be looking at what instruction is executing at what time instant. Okay, so here you can see the total execution time for 4 loads is reduced to 3.5 hours. So speed up for 4 loads is 2.3, which is very less. If you run the load cycles non-stop, you will see the speed up would become equivalent to the total number of stages. Okay, so if we follow the single cycle, the 800 picosecond cycle time, so we have 3 instructions here. The first instruction will complete in 800 picoseconds, or whatever the unit is, and second one is again will take 800 picoseconds, and third one is again 800 picoseconds. So when do you think the 4th instruction will start executing? It's a very simple thing. The 4th instruction will start executing after how much time lapsed? 2400 picoseconds, right? So here the single cycle is 800 picoseconds. So first 3 instructions are executed in 2400 picoseconds, and the 4th one will start at the 2400, right? If we compare it with the pipeline implementation, you can see it here. The cycle time is 200 picosecond. Why 200 picosecond? Now the cycle time is not 800 picosecond. Here the cycle time is 200 picosecond. So we have to use the cycle time that must be long enough to accommodate the slowest operation. What is the slowest operation here? Is fetching the data from the memory or ALU, whatever is lengthier, you have to use that cycle time. Okay, so here in this example, 200 picosecond is the amount of time which is taken up by these units, which is the lengthiest time. Okay, yep.
Why wouldn't we use
800 is the total time. So we were using the 800 here because it was a single cycle processor. So everything completes in 800 picoseconds. Okay, but here in this example, load instruction is taking 800 picoseconds. But what about R type? I have already discussed this. R type would complete in 600 picoseconds. So the 200 picosecond would be left unused. So it will remain idle. So that is why we, instead of going for the single cycle processor, we are enhancing the performance of the processor by the pipelining concept, yes.
So what is like a gap in between the test?
Yeah, so I'll come to that point in a while. First of all, do you understand that why 200 picosecond is the cycle time in pipeline processor? Of course, these are the just exemplary numbers. It could be different, anything. For example, if I give you a chart like this, and if I specify 350 picosecond, for example, so 350 picosecond should be the cycle time in the pipeline processor. Okay, so here the first three instructions are executed in what time? It's executed in 1400 picoseconds. So there is a thing that needs to be discussed here. So registers, we have already talked about that only one thing can be done at a time. Like when we were discussing about why we split the memory into instruction memory and data memory, remember the discussion? Why did we do that? Because we cannot read and write at the same time in the same memory. Okay, we can either read or write. So here we have only one register. So the designer came up with an idea of writing the register, writing into the register in the first half of the clock cycle, and reading the register in the second half of the clock cycle. So this is a clock cycle here, right? So this at this edge of the clock, we will be writing into the register. So write register. I'm sorry, I forgot to bring my iPad here, so I will probably take a picture and put it in the video. And in this cycle, in the first half of the clock cycle, we will be writing into the register, and in the negative half of the clock cycle, we will be reading the register. Okay? So if you look at this diagram here, when we are running a series of instructions, so here you can see this instruction is writing some data into X1. And at this same instant of time, between 800 to 1000 picoseconds, you see another instruction is executed, which is fetching the data, which has to fetch the data from the register. Okay? So because of this implementation, this instruction can write the data during the same time in the first half of the clock cycle, and during this same clock cycle, we can read the register for this instruction. Okay, so we do not need to halt the clock cycle. You get that? At the same clock cycle, in this same clock cycle, we are writing the register. This instruction writes the register, and this instruction is also reading the register in the next half of the clock cycle. So in this particular example, you see that you are writing into X1, but what if the same instruction at this instant would be reading from the same register? Although it is not the case here, but we would be able to read the updated data from the register because of this arrangement, writing in the first half and reading into the next half of the clock cycle. Okay, and that is actually an issue in the performance of pipelining. We will get to that later.